Hey guys, my name is Cesar Hernandez, and I'll be discussing today about neural networks and universal approximation theorem. So we're going to go over the introduction, the neural networks, universal approximation theorem, and our conclusion. Introduction is we're going to learn about the universal approximation theorem. Is a fundamental concept in machine learning. What are our weights? What are biases? And just to give you a little background information, so we're going to explore the fundamental concept of a neural network, explaining their structures, their functions, and the process of learning through a simple example of digit recognition. It breaks down the components of a neural network, including neurons, layers, weights, and biases. We'll also discuss the significance of these elements in the context of machine learning. What is a neural network? Neural networks are inspired by the human brain and consist of interconnected units called neurons. So each neuron holds a number-specific value between the ranges of 0 and 1, which is represented in its activation level. In the example of 3 brown, 1 blue, is going to be the example of recognized handwritten digits. The network starts with 784 neurons corresponding to each pixel in a 28 by 28 image input. The last layer consists of 10 neurons, each representing a digit from 0 to 9. And depending on the model and type of network, some networks may have more than one hidden layer, and so forth. The layers of a network consist of the input, a hidden layer, and the output. For the example, from the example from the 3 brown, 1 blue, the container holds 784 neurons, each representing a pixel grayscale value between 0 and 1. The hidden layer has 2 inputs, which consist of 16 neurons, and the output consists of 10 neurons. How a neural network works is that there is a public network and a hidden layer. The public is responsible for the activation in one layer, influence the activation in the next. When an image is fed into the network, the activations from the input layer trigger specific patterns in the hidden layer, ultimately leading to an output in the final layer. The brightest neuron in the output layer indicates the network's predictions from the number represented in the image. The hidden layer are crucial for recognizing pattern. For instance, when recognizing a digit like 9, the network might identify components such as loops and lines. Ideally, neurons in the second layer would activate in response to these subcomponents, allowing the network to learn which combination responds to significant digits. The mechanics of learning. So what does the weight and bias do in a neural network? Why are they important? So we're going to learn about neural networks involves adjusting the weights and biases associated with the connections between neurons. Each connection has a weight that determines the influence of the next layer's activation. The goal is to find the right settings for these weights and biases so that the network can work accurately to recognize the digits. What are weights? So weights are numerical values that are assigned and are connected between each neuron, which determines the influence on one neuron's activation has on the other. So it means essentially that if one neuron is higher than the other, it's going to tweak it to be not fully 100%, but matching the other weights. And the biases are additional numbers which are added to the weighted sum at activation. And this creates a threshold for accuracy, right? So the higher the number it is, the higher the prediction it's trying to convince us of. And if it's lower, then that means it's a bad prediction. A function of a neural network. So the function of a neural network comes down to its core component. The process involves a multiple matrix vector product, a dot product, and activation functions such as a sigmoid function, which squashes the outputs between the range of 0. The sigmoid function is commonly used to determine the neuron's activation. However, in modern networks, they often utilize ReLU, which stands for Rectified Linear Unit Function, which simplifies training and improves performance in deep networks. The learning outcome is that neural networks are powerful tools for recognizing patterns and making predictions. By understanding their structure and the learning process, we can appreciate the complexity behind tasks like digit recognition. And the next, we'll learn how neural networks learn and redefine their capabilities. So now we're going to talk about universal approximation theorem, which states that a feedward neural network with a single hidden layer can approximate any continuous function to any degree of accuracy, provided the activation function is non-constant, continuous, and bounded. So what is the universal approximation theorem? In general, it states that the feedward neural network with a single hidden layer containing a finite number of neurons can approximate any continuous function with a subset of input values to any degree of accuracy. The key condition for the approximation are the activation functions used in the network must be non-constant, continuous, and bounded. So the layers for universal approximation theorem go the feedward forward, the single layer, the finite number of neurons, and the continuous function. A little bit of each of these is that the single layer must have a single layer for an input and an output. It has to have a finite number of neurons in the hidden layer, and it has to be a continuous function that does not have any abrupt changes in its values. The condition for the theorem is that if it has all those layers, the feedward forward, the single hidden layer, the finite number of neurons, and is continuous, and has non-constant activation functions, such that ReLU is non-constant and bounded, then the conditions are met for the approximation theorem. The limitations of the theorem is that the approximation value is only valid within a defined range of inputs. For example, our approximation was effective between x equals -2 and x is 4, but outside the range, the accuracy diminishes significantly. So meaning if we don't have a designated range, or if we go above that range, our predictions and accuracy will be affected by that. The importance of an activation function is crucial in the ability for neural networks to approximate complex functions. Without activation functions like ReLU, the network would be only able to represent linear functions, which will limit its capability.